Okay, so today we're going to be looking at section 7.1, solving linear systems. Okay, so let's look at this and see what's going on. So what is a linear system of equations? What does it mean to be a solution to this type of system? Okay, so a system is just basically a collection of more than one linear equations. Okay, and so how do I find a solution if there's more than one equation? What does that mean? Okay, so let's take a look. So a linear equation, ax plus by equals c, is a collection of all the points x and y that make this equation true. So all the equations, all the points that make that equation true are considered solutions to that equation. A linear system is just a collection of two or more linear equations. And so the solution to a linear system is the point or points, okay? If it's linear, there's going to be, could be more than one point, and this, I'll tell you about that a little bit later, that make all the equations in the system true. So every point that makes that equation true is a solution to that equation. And then, so a system is, there's more than one equation, and I'm looking for all the points that make all the equations true at the same time. Okay, and there's three ways that we can go about trying to solve a system. Okay, the least accurate is the graphing method, a graphical solution, because a graphical solution, although it can give you the solution, sometimes it's very difficult to identify what that solution is. And so really what you're doing with a graphical is you're looking for an approximation to the solution to the system. Okay. We can approximate the solutions to a system of linear equations by graphing all the equations in the system and identifying any point or points of intersection. Okay. You can confirm if it's a solution by then substituting it into all the equations to make sure it's true for all equations. But that's what you're looking for, is an approximation. So we're going to go ahead and do an example to show you how I can find a solution to a system by graphing. And I have one right here. Got it set up for us. I want to find an approximate solution by graphing this system right here, which is one equation is 2 times x plus 10. The other one is a negative 1/4 x plus 1. They're both lines. I'm going to graph them both. So what you basically do is you just graph each line. You can graph the line any way that you know how. I'm just going to show you by a table format, just to be consistent with what I've always done. Let me get my pencil working. So in the top equation right here, if I plug in 0, I'm going to get 10. If I plug in 1, I'm going to get 12. And if I plug in negative 1, I'm going to get an 8. Okay? And then I can see that the rate of change is a 2 each time, so I can find more points if I need to. The bottom equation has a slope of negative 1/4, so I'm going to plug in numbers that eliminate that fraction. That's why you see a 4 and a negative 4 here. If I plug in 0, I'll get 1. If I plug in 4, I'm going to get 0. And if I plug in negative 4 over here, then I'm going to get a 2. And so I'm just going to graph each of these lines, and then I'm going to draw them. So the first one is I have a y-intercept at 10. At 1, I have a 12, so that'll be up here. At negative 1, I have an 8. And so I can see that a slope of 2. I can keep this pattern going backwards down here, just doing a slope of down 2, back 1. That is a slope of 2 also. Just continuing this process, I can get a nice, accurate line drawn. And that's what I'm looking for right here. So let me draw that line. The more accurate you are, the better your approximation is going to be. Take into consideration the thickness of your pencil. Try and make the line go through the corners of the grid, because if you're off slightly, it will continue that error and get worse and worse the farther out you go. So this is the first line. I'm going to come back and label it all later. Graph this one, 0, 1, 4, 0, negative 4, 2, and look at what we see right there. So we're looking for points of intersection. I think we just found one. So draw everything up nice and accurate as possible, just to make sure, because you do not know exactly, because of a graph is just an approximation. So there's that line. So in graphing a system, there's a couple things we want to do. Look for the point of intersection. I know that this point is on both of these graphs. So this point right here is -4, 2. Always want to label the point of intersection. And then one more point on each graph. Usually you just do like the y-intercept or something that's nice and easy to see. You want to name each line. So this is y equals -1/4 x plus 1, and label this line y equals 2x plus 10. So that graph is what it should look like, okay? And then you want to identify your solution. You just can't stop right here and call that my solution. You need to actually identify your solution. You can call this answer or solution. And the solution is the point of intersection, which we see is going to be -4, 2. So that is my solution, -4, 2. That is the point of intersection of these two graphs. And I can take these points and plug them in. I know it works in the bottom one because it's in my table. If I take -4 and plug it into there, I'm going to get -8. -8 plus 10 is 2. So indeed, this point right here is a solution for both of those graphs. That's the graphical solution. You graph it and look for the points of intersection. Be careful. Draw as accurately as you possibly can so that you get points that are nice and neat to see. If it lands in between, that's why it's called an approximation. You just approximate what you think it is, usually in a decimal format to the nearest 10th, 1 decimal place, just as best as you possibly can. Okay, so that's the graphical one, but that takes a lot of time. We want to know, is there a way that I can do this differently? Let me zoom out a little bit so you can see everything at once, for those who might be copying this down. Okay, so is there another way? Well, before I go into that, let's talk about some special cases that are going to arise. We kind of talked about up here when we talked about this, how do I have plural number of solutions with a linear system? Okay, so I'm going to move that. I want to talk about some special cases. I'll just show you this right here. So there's the example we just did. And some processes here. I'm going to stop and pause here for a second, for those who might be copying this stuff down. So draw all the lines, show where they intersect, label these points, label 2 points, and name each line, identify the solution. That's what I just told you. What are the special cases? Well, if a 2-equation system, if I have a 2-equation system and a 2-equation system, if both lines are the same line, although they may be written in different forms, but when you graph them, it becomes the exact same line, then the 2 lines intersect at every single point. Like, think of it as one line on top of the other line. That means everywhere along there, they intersect. So that system has what's called infinite solutions. This is where you would have a case where you have more than one, if they are the same line. Well, what if I have in a 2 or more system, all the functions, all the lines never intersect? Well, if they never intersect, then that system is said to have no solutions, because the solutions are where they intersect. And so if they have no solutions, they don't intersect, there's no solutions. An example of this would be if I have 2 lines that are parallel. Later on, when we get into more advanced systems, there can be, just as long as there's no intersecting points, then there is no solutions. They don't have to just, we're going to go beyond linear systems. So, but in a 2 lines, if they are parallel, they never cross, they never touch. That is an example of a no solutions. So keep that in mind. If the lines are parallel, no solutions. If they are the same line, infinite solutions. Now, because a graphical system solution to a system equation is only an approximate solution, we need to be more accurate. I need to be able to find it exactly, especially when it lands not on a nice grid point, but somewhere in between with there's a fraction involved. Okay, I need to be able to find that, and so now we're going to look at the algebraic solutions. Okay, there are two methods for solving a system of linear equations. One is called substitution, the other one is called elimination. The substitution method is the most useful from this point going forward. When you go to other classes and other stuff, even when we do the system of equations that's non-linear, okay, substitution is the technique you're going to use. Elimination technique is convenient in some cases, and it really is used more often in a branch of mathematics that comes from this study of this kind of systems, linear systems, called linear algebra, where they go into linear elimination method in much more detail, and a whole branch of mathematics is created based off of this. And beyond non-linear systems, okay, elimination technique is not very useful, in my opinion. Okay, so here is the substitution method, and we're going to do an example as I show you the steps that we're going to follow. Okay, so substitution is the preferred method for solving any system. Sometimes it's a little bit more challenging, but I've shown you both so that you can use whichever one that you feel more comfortable with for linear systems. Please remember that they're also going to be asked to solve systems that are non-linear, and substitution is the technique you're going to want to use. So here's how it works. Here's my system. You're going to solve one of these equations for one of the variables. There's two equations here. The variables are x and y. You pick one of the variables. It does not matter which one. And you substitute that, and then you solve for it. So you can do either way you want. If I want to, I'll take this one right here, since x is no number in front of x. I'm going to take that. I'm going to solve for this one for x by subtracting 2y to both sides. If I subtract 2y to both sides, then this tells me that x will equal 6 minus 2y. And then I usually put this in the parentheses. Okay? So I now have this x solved for this, and I'm going to substitute this quantity into the other equation for x. So then I'm going to rewrite the top equation using parentheses, because every time I substitute, you always put things in parentheses. Plug in what that x stood for, write all the rest of the stuff down, and now I have one equation with one variable in it. And then I can solve this using our solving techniques. So we distribute to get rid of the parentheses. So negative 18 plus 6y minus y equals 7. Combining like terms, I get 5y minus 18 equals 7. Add the 18. And so 5y equals 25. And divide by 5, y equals 5. Take that number, plug it into the original one. You can plug it into this one over here, okay? But if you plug it into this one, you'll start seeing whether or not something's going to work or not. But either way is fine. It doesn't matter. And so x plus 2 times 5 equals 6. So x plus 10 equals 6. And so x equals negative 4. That's not my solution. You write your solution as a point. So your answer, and you can just do A and S, answer is the point, negative 4, 5. That is my answer, and you should check it in the original equations to make sure that you are right. There is no reason for you to be wrong when you can easily check it. Negative 3 times negative 4 minus 5, is that 7? Well, that right there is 12 minus 5. Yes, indeed, that is 7. And then this one right here, negative 4 plus 2 times 5, is that 6? Well, that's 10 minus 4. That is indeed 6. You have confirmed that that is indeed my answer. Okay? This is the substitution method. All right? So let's look at the next one, which is the elimination method. And I have that one over here. We're going to solve this example right here. So let's talk about how this works. So elimination. This process works best for systems of linear equations only. It is the foundations for a branch of mathematics called linear algebra. Okay? So that's what I said earlier. So the elimination method is a little bit more involved to start. Okay? But once you understand the process, it goes by very quickly. So what we're going to do is we're going to do, like I said, elimination. We're going to choose a variable to eliminate. It does not matter which one you choose, but make your work a little bit easier. Try to choose ones that maybe already differ in sign, like one's positive and one's negative, like this. Okay. What we're going to do is we're going to add the two equations together by combining like terms, and I want whatever letter I choose to become a zero when I add them together. So I want them to be opposite numbers. So that's what it says. We're going to multiply each equation if needed. Sometimes you only got to multiply to one equation. We're going to multiply by a number. It doesn't necessarily have to be the same number. But our goal is to make the variable we chose to eliminate, I want these coefficients to be opposite numbers. So right now this is a -3 and that's a +2. I need to think of a number that both of these will divide into. So 6. You can also just use the number that multiply them together. So 3 times 2 is 6. So I want to make this a -6 and this a +6. And so what do I need to multiply to each equation to make that happen? So this equation, I need to multiply it by 2. This equation, I multiply by 3. This, when I distribute, will become a -6. This, when I distribute, will become +6. And those numbers then will be eliminated. That's what we're trying to accomplish. Once you've determined what you're going to multiply by, this number out here can be positive, could be negative. You may only need to multiply one equation by a number. But whatever you do, make sure you multiply it to both sides. And when you multiply it, rewrite your system. So this right here is going to become 8x minus 6y equals, and don't forget this one on this side, -18. You got to do it to all the terms on both sides. 3 times 3 is 9. 3 times 2 is 6. 3 times -11 is -33. So here's my system that has been multiplied by all those numbers out front, and I'm going to add these two numbers, these two equations together. When I add them by combining like terms, this becomes 17. This is now eliminated. +6 plus a -6 is 0, so this is 0. The equal sign comes down, and then we add these up right here. Okay, adding those up, we get what? 1, 51, and negative. Okay, and so now I have this system right here that I can solve. Divide both sides by 17, and I get x equals a -3. And once I have this value right here, then I take this number and I substitute it back into an original equation, one of the original ones. It does not matter which one you choose. Okay, so I can choose the top one. That'd be 4 times a -3 minus 3 times y equals -9. And then I solve this for the y. -12 minus 3y is -9. Add the 12. And so -3y equals 3 divided by -3, so y equals -1. Once I have that, my answer is written as a point, -3, -1. And then you would check each of those to confirm that that is indeed true. Okay? This is the elimination method. Here's what I have written down at the bottom here so you can see the steps for those who are writing it down. Choose one variable to eliminate. Multiply each equation if needed by a number so that the coefficients of the variable you want to eliminate are opposite multiples of each other. The number used for each equation can be different. You're going to add the two equations. You should now have only one equation with one variable. Solve for the variable. Then substitute this number into an original equation for the second variable value, and then write your answer as a point. And that's what we did right here. You can see, here's what I had written out right here. Choose a variable. So I chose the variable y to eliminate because they are already opposite in sign. Okay. I want to make the coefficients positive and negative 6. So then I multiplied by these things by 2 and 3 so that that occurs. Add the two equations and then solve it all out. Now, the special cases. When we did talk about the special cases with the graphing technique, we talked about how the graphs would look. If one equation is exactly the same as the other equation, when I graph it, then it's an infinite number of solutions. And if the graphs do not cross or never intersect, then that is no solution. Well, what is it going to look like when I solve it algebraically? Well, that's what I have written right here. Okay, this works for either method. If I have the same line, what's going to happen is I'm going to do this, eliminate, let's look at it from the point of view of the substitution method. So I did this part right here, or the elimination method, and then I add these two equations together, and what's going to happen is not only is this variable going to be eliminated, but so is this one. All the variables will disappear. Okay? This is when that happens, you know you have a special case. Then the question becomes, is it going to be an infinite number of solutions special case or a no solution special case? So whether I'm doing elimination or substitution, in substitution, I plug this in, right? I plug this into the second equation, and then I multiply it and combine like terms, and what will happen is the variable will disappear. There'll be no variable here. You'll just have some number equal to another number, okay? So in this case, it would be like negative 18 equals 7, because the y's would have been gone. Well, if the variables disappear and you're left with a true statement, that means you'll get a number, whatever that number is, equal to the exact same number, 5 equal to 5, okay? Then you know that means you have an infinite solution. But if you do a process of solving, whether substitution or elimination, and the variables disappear, and you're left with a false statement, meaning you'll get a number equal to a different number, like a negative 18 equals a 7, then you know that means you have no solution. The lines did not cross. Okay, so make sure you are aware of these two processes here so that when they come up, you are familiar with how to address your answer. Okay, if it is a false statement, no solution. A true statement is infinite solutions when we talk about a system. So those are the three methods. You'll be required to be able to show me all three methods on a system. So I'll give you a system and ask you to solve it graphically using substitution technique and then also elimination technique, the same system. So be prepared for that, and we'll do more examples in class.